All right, section 8.1. Chapter 8 is all about the quantum model of the atom. And in order to kind of set that up, we have to start talking about light. And so we're going to go through a couple of different, brief introduction, and then we got a couple of different practice problems. And I'll tell you which ones are the practice problems that you'll probably expect a little bit. This has a good number of slides, but hopefully it won't take too long. Okay, so light is a form of energy that can be described as a moving wave of magnetic and electrical potential. Okay, so light is a moving wave. Visible light is the light that can be perceived by the human eye, and light can be refracted through a prism. So we've got three different terms: light, visible light, a specific range of light, and then light can be refracted through a prism. Here we've got an example of visible light being refracted through a prism. And what this shows us is that the different color components of a particular beam of light. Okay, so properties of light. One property is that you need to know, to understand the properties of light, you need to understand that there are these two terms: wavelength, represented by this symbol right here, which is lambda. That's the difference, or that's the distance between two corresponding points on a wave. Frequency, represented by this, it's not mu, but it is nu. This looks like a V, and I will sometimes refer to it as V, but the appropriate terminology is nu. So lambda is the number of crests that pass a given point per second. The inverse seconds, or s to the negative first, is also known as hertz, or Hz. You might be familiar with that with respect to Wi-Fi, and those would be waves, and the frequency of those waves would be in megahertz or something like that. So frequency times wavelength, so nu times lambda, equals a constant c, which is the speed of light, 2.998 times 10 to the 8th meters per second. This is a number that I recommend becoming very familiar with, because you'll need it for these sorts of calculations. Please note that the units for speed of light are in meters per second. And what this shows is that it can be written as m times s to the negative first. Okay, so this right here would be basically a single wavelength from this point, this point to the corresponding point. One complete wavelength has been completed, starting at point A and ending at point B. So that's one wavelength. Now, in the event that you imagine a particle traveling along this line, and let's say you set a timer for 1 second, and it starts here and it ends here. Well, that would be, over the course of 1 second, that would be, that would be approximately 0.5 wavelengths per second. So s to the negative first. So 0.5 completed wavelengths are, well, half a wavelength is completed in 1 second. Now, this right here is a good practice problem that you're definitely going to see from time to time. Calculate the wavelength. Okay, so now remember, wavelength is going to be represented in meters, or more commonly nanometers. Calculate the wavelength of light that corresponds to a frequency of 7.30 times 10 to the 14th per second. So our units there, let's go ahead and write this out: 7.30 times 10 to the 14th. Now, if you remember, we had nu times lambda equals c. So this is frequency times wavelength, WL. I'm just going to write shorthand as wavelength. And then the c is speed of light. So this is a constant, 2.998 times 10 to the 8th meters per second. This is our unknown. All that we really need to do is rearrange this to say wavelength is equal to c divided by v. So 2.998 times 10 to the 8th divided by 7.30 times 10 to the 14th equals, well, our units are going to be in meters, and 2.998 times 10 to the 8th divided by 7.30 times 10 to the 14th. That is going to be 4.10 times 10 to the negative 7th meters. Now, like I said, you're going to see this in meters as well as in nanometers. So what I recommend that you do is whenever you see a number like this, where it's in scientific notation where there's one number in front of the decimal, two to the right, that is going to appear as 410 nanometers. So whenever you see this negative 7th, I would be negative to the negative 7th meters. I'd be ready to throw that straight into 410 or into nanometers, because 1 meter is equal to 1 times 10 to the 9th nanometers. All right, the electromagnetic spectrum includes a number of different things. It includes radio waves, microwaves, infrared light, visible light, which is where we generally are going to stay, ultraviolet light, X-rays, and gamma rays. All of these different forms of light differ only in wavelength and frequencies. It's the exact same thing, but it's either going very, very fast or it's going slow and over a long wavelength. Longer wavelengths are associated with lower frequencies and low energy forms of light, such as radio waves and microwaves. Shorter wavelengths are associated with a higher frequency and higher energy forms of light, such as X-rays and gamma rays. So if you think about the Incredible Hulk, he was impacted by gamma rays. He was impacted by high frequency short waves. This is our, I guess, kind of visual for displaying difference in wavelength and frequency. So we've got low energy to high energy. We've got long wavelengths with low frequency associated with low energy. We've got short wavelengths associated with high frequency associated with high energy. And our range is from long radio waves all the way up to gamma rays. Now, if you think about, well, what causes or what has a high amount of energy, well, we've got some devices that you may be familiar with. An AM radio, for instance, has very low energy waves. Broadcast TV or FM radio has slightly higher energy. Cell phones, microwaves, those are going to be higher energy, and all the way up to a sun lamp, which is going to be significantly higher energy with shorter frequency higher frequency and short wavelengths. Light absorption and emission, matter and energy are constantly interacting with one another. Light can be absorbed, and that is going to occur when an atom absorbs light energy from the surrounding and gains energy. Now, light emission, on the other hand, is when an atom has excess energy and gives off energy by emitting light. So it's in what's referred to as an excited state, and it releases energy and produces some or emits some form of light. Now, the photoelectric effect is something that you're going to have some calculations associated with it. In some experiments, light behaves like a wave, but in other experiments, light behaves like a stream of tiny particles. Okay, so if you shine a beam of light onto a metal surface in a vacuum, electrons will be ejected. The light must be of a specific minimum threshold energy, and shining light of higher energy does not increase the number of electrons ejected. However, the brightness of that light is proportional to the number of electrons that are emitted. This phenomenon is known as the photoelectric effect, and the electrons emitted are known as photoelectrons. Now, here's a visual of that photoelectric effect. We have light of a certain wavelength onto this metal surface, and that causes electrons from this metal surface to be ejected. Now, Einstein's explanation for this won him the Nobel Prize in 1921, and he proposed that light behaves as tiny individual packets of energy, known as photons. Each packet of light, if it contains enough energy, knocks an electron from that metal surface. Increasing the brightness increases the number of light packets and results in more electrons being ejected. So if you have a light that's very intense, like I think maybe this one's more accessible. Yeah, well, I've got one next to my desk and it's particularly bright. Compared to like a dim light like this or something like that. This is not going to produce a high amount of energy, and so if it displaces any electrons, it's going to be a small number compared to a very bright light, which is going to eject a large number. The wavelength of those beams of light are identical. If the energy of the light packet is below the minimum threshold required to free an electron, no electrons are emitted. So low energy is not going to cause any electrons to be ejected. Now, this dual nature of light, its ability to act as a wave and a particle, so it can be both a wave and a stream of particles. So it has this wave-like activity function, whatever you want to say. However, in any given experiment, it will behave only as one or the other. So this is known as the wave-particle duality of light. Now, the particles of light are also known as photons. Low energy photons correspond to light with long wavelengths and low frequency. High energy photons correspond to light with a short wavelength and therefore a high frequency. So what we have is kind of a summary of E is equal to HV. Okay, so that V, or that nu, that's our frequency. H is representative of Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. So think about the units for frequency. Those are negative or inverse seconds. When you multiply joule seconds by inverse seconds, well, then those seconds are effectively going to cancel out because this right here is the same as 1 over seconds. So it's like it's in the denominator. So you're going to be left with joules. But this draws a correlation between frequency and energy associated with those waves, or those waves. So what color is a photon that has an energy of 3.28 times 10 to the negative 19th joules? Okay, so our equation is E equals H nu. This H is 6.6, oopsies. Yeah. I'll erase that too. 6.626 times 10 to the negative 34th joule seconds. That is equal to, sorry, I made a mistake there. So that's our H. Our frequency, we don't know yet. But do we know the energy? Yes, we do. 3.28 times 10 to the negative 19th. Now, you might look at this and say, okay, well, how do I get from energy to color? Well, the way that you're going to do that is you're going to solve for frequency. And then what you're going to be able to do is you're going to be able to say, well, lambda times frequency is equal to the speed of light. So when we solve for frequency, we'll be able to divide by mu. And now all of a sudden we have wavelength, which we can associate with a color, is equal to C, which is a constant, 2.998 times 10 to the 8th, divided by whatever frequency I get. So I'm going to go ahead and solve this. (626) times 10 to the negative 34th. So I'll plug this in. 3.28 times 10 to the negative 19th divided by 6.626 negative 34th, and I get a frequency that is 4.95 times 10 to the 14th inverse seconds. So 4.95 times 10 to the 14th. Okay, so now wavelength 2.998 times 10 to the 8th divided by 4.95 times 10 to the 14th equals 6.056 times 10 to the negative 7th. That's in meters. So I can change this to 606 nanometers. And this is the sort of question that if you had it on an exam, I would give you reference colors. But I can tell you that 606 nanometers is orangish. I'm just going to say orange-ish. And that would be good. Okay, so once you've solved that, once you've seen a correlation between frequency and energy, we get into this work function. The work function is the minimum energy necessary to remove an electron from the surface of the material in a vacuum. So think about that as if you shine blue light versus red light at a substance. Will blue light eject a, will blue light eject a electron, or will the red light do it, or will they both do that? So different metals have different values for their work functions. The work function is related to the threshold frequency, that minimum frequency of light that can have, or that can eject electrons. Wavelength can be determined from frequency. Okay, so that's what we're looking at. And as soon as we connect it to wavelength, then we're connecting to it to a color. Okay, so we have this equation. HV is equal to phi. Wavelength can be determined from that frequency where we say HC divided by our wavelength is equal to 5. Now, sodium metal has a work function equal to 3.78 times 10 to the negative 19th joules. So if you remember what we were just looking at, the equation that we had was HV is equal to phi, and we also looked at HC divided by lambda equals phi. Okay, so what minimum frequency of energy is needed to remove a surface electron from sodium? To what wavelength of light does this correspond to? So effectively what we can say is we're looking at, or we're trying to answer two questions. A, what frequency, and B, what wavelength. So what I'm going to do is I'm going to say 3.78 times 10 to the negative 19th is equal to my phi. So I'll rewrite this as 3.78 times 10 to the negative 19th joules is equal to, well, H nu. Now what I want to do is I want to go ahead and isolate nu. And I can do that by simply saying, well, dividing each side by H, because I know that H is equal to 6.626 times 10 to the negative 34th joule seconds. So I'll divide this by 6.626 times 10 to the negative 34th. So 3.78 times 10 to the negative 19th divided by 6.626 times 10 to the negative 34th. Our frequency here is equal to 5.70 times 10 to the 14th. Okay. Now, that gives me that piece of information. So this solves for A, basically. But this doesn't solve for B. However, I could plug it into my equation of lambda times frequency equals speed of light, c. Or what I could do is just go ahead and use this equation right here with it kind of all piled into that. Okay, so what I'm going to do is for B, I'm going to say H is 6.626 times 10 to the negative 34th. Multiply that by 2.998 times 10 to the 8th. And I got to do a little bit of algebra to rearrange this equation. So lambda, multiply each side by lambda, gets rid of it there, divide it by phi, and so I rearrange this to say HC over phi is equal to lambda. So I've got the HC right here. Now I'm going to divide each side by phi, which is my work function, this 3-point work function. It's like you got to go to a work function at the golf course. Anyway, this 3.78 times 10 to the negative 19th. That's going to leave me with lambda, and I can go ahead and plug this in. 6.626 times 10 to the negative 34th times 2.998 times 10 to the 8th. Divide that by 3.78 times 10 to the negative 19th, and that gives me 5.25 times 10 to the negative 7th. Remember, that's in meters. That wavelength, I'm going to rewrite this as 525 nanometers. And for reference, 525 nanometers corresponds to kind of a bluish color. Well, that about sums it up. And that's all the stuff that I wanted to go over for this 8.1. And I know this is a little bit lengthier than our normal videos. Sorry about that, but they were all very closely connected, all these different examples. I hope this is helpful, and you got this.